All right. Section 2 of Chapter 2 is still talking about polynomial functions. In the first section, the main polynomial function that you dealt with there would be a quadratic one. This section is going to talk about polynomial functions of higher degree. So we are still looking at polynomial function in that form. Ax to the n plus bx to the n minus 1 plus all the way down to dx plus e. The number of terms that it can have, it all depends on the type of equation or function that you're going to see. And again, a few things about it. The largest exponent is the degree. With the degree, then, there's a value called a, and that is the leading coefficient. And there's also the constant term, which does not have a variable with it. In a polynomial function, if you were to sketch a graph of it, the polynomial function would be smooth and continuous. They would not have breaks in them. They wouldn't have like sharp turns. But it would be something maybe like so. Could do something like this. And possibly even that. There are three examples of what a polynomial function would look like, provided that this right here, if we blow this little section up, it doesn't come to a point like this. If it comes to a point like that, it's not a polynomial function. If it's a flowing, smooth, continuous thing, then it is. Here are some examples of things that would not be polynomial functions. That is not smooth and continuous because it is broken right here at the y-axis. And yet another one would be something that maybe does this. Because that right there, there's just a point. So that's the first thing you need to know about any polynomial function when you're drawing them. Make them smooth, make them continue on forever. Now, the importance of the constant and the leading coefficient are many. The constant tells you where it crosses the y-axis. It's your y-intercept. It will also help you find some things later on that we will get to. Leading coefficient helps you in defining what the function looks like. If the degree of a polynomial function is even, and a, the leading coefficient, is positive, then both ends will go up to infinity. If the degree is even, and the leading coefficient a is negative, then both ends will go down to a negative infinity. And so here's an example of a polynomial function that would have an even degree because both ends go up or both go down. This one could be a degree 5, but that we're not sure of. Now, if the degree is odd, and the leading coefficient is positive, then we have the left end going to negative infinity and the right end going to infinity. And if the leading coefficient is negative, then the left end will go towards infinity and the right end will go to a negative infinity. These statements here, they are important in helping you understand what the graph of it looks like and how to make your viewing window bigger or smaller depending on what type of polynomial function you have and what type of degree it is. The second thing about a polynomial function is the degree of it. The degree of it would tell you at most it has n roots. So if the degree is 4, then it has at most 4 roots. They are also called factors of the polynomial function. They are zeros of the polynomial function, or they can be x-intercepts. All of these words basically mean the same thing. It's just a different way to ask it. And since it has n, at most n roots, it has to have n minus 1 terms. So in our example here, x to the 4th plus 8x squared plus 3x minus 25, the leading coefficient is 1, and the constant is 25 negative. So we know that it crosses at a negative 25 because it has a leading coefficient that is positive and it's a 4th degree polynomial. Both ends are going to be going up. Crosses at a negative 25, and it could possibly do this where it just comes down, kind of flattens out for a little while, and then curves back up. There also could be a little wave action to it, so maybe it does this. Something along those lines. Now, in a polynomial function, once you graph it, say you have this. No, let's change this just a little bit, make it easier for us. This place here and that place there are minimums, relative minimums. The one on the left, this one, not only is it a relative minimum, it can also be called an absolute minimum. Because it is the smallest value in your polynomial function. Here, this is a relative maximum. And with this, there is no absolute maximum because both ends of it are going up. So it's going to reach some, it's going to continue to get bigger and bigger. Another example of a 4th degree polynomial function would be maybe something that does here and that, where there is no wave here in the second one. So this point right here would be an absolute minimum, and somewhere in here would be your relative maximum. Now then, with most polynomial functions and the ones actually here that I've drawn, all of them cross the x-axis at some point. Which then they are called roots. They are also called x-intercepts of the polynomial function. They're zeros of the polynomial function, and if you know those things, then they become factors of the polynomial function. So if x minus 2 is a root of some polynomial function, then we know that x minus 2 is a factor. If a negative 4 is a root, then we know that x plus 4 is a factor. And finally, if 1/3 is a root, then either x plus 1/3 or 3x plus 1. Because whatever the root is, the factor is the opposite. Or whatever the factor is, the root is the opposite. Now, they will also talk about multiplicity. Of roots. And they could say 4 is a root of multiplicity 3. If that is the case, then you know that you have factors of x minus 4 times x minus 4 times x minus 4. Or you can write x minus 4 to the third power. Like that. Now, when you have a root that has a multiplicity of whatever, if the multiplicity is odd, the graph will run through that point. So like, for example, with this one, because 4 is a root 3 times, this coordinate, the graph, whether it's going like this, maybe it comes down like this and goes back up, and then it turns like so, it has to go through that point of 4. Or it could even go the other way. You could have something that does this. It really doesn't matter. But just know that if the multiplicity is odd, it runs through the point. If the multiplicity is even, then it will just touch that particular point. So if we were to say 2 is a root, with multiplicity of 3. No, I don't want 3. Let's try 4. So now we know here at 2, there is a root. Since it is a multiplicity of 4, that's even, it's going to just touch that point. So it will either go up or down. So we'll have it like so. Maybe it does this. Or it could even be the other way. Where it just touches 4 and then continues back to the other direction. Another example would be if negative 3 was a root with a multiplicity of 4, then we're talking about x plus 3 to the 4th power. And if a negative 2 is a root, or a positive 2 is a root with a multiplicity of 5, then you would have x minus 2 to the 5th. And plotting those, negative 3 would be here, a positive 2 would be here, and since a negative 3 was to the 4th power, so this point is just going to touch, and the 2, because it is to the 5th power, is going to pass through. So we maybe have to do something like this, and then curve it back down to go like that. So here it says it's a 7th degree polynomial function, but it only shows 2 roots. So because a negative 1 is a root, x plus 1 is going to be a factor. And because 6 is a root, x minus 6 is a factor. Now, from our previous window, if this passes through, then the exponent for this has to be odd. And because it touches on this one, the exponent has to be even. So therefore, because it's the 7th degree polynomial, this could be to the 3rd, this one could be to the 4th. It could also be x plus 1 to the 1st, and x minus 6 to the 6th. And similarly, this could be the 5th, and that would be the 2nd. And that's how you'd get a 7th degree polynomial. Now, if you were to try to enter this into your calculator, you could do it this way. And that would be fine. It'll do all the math then for you. Finally, in your book on page 111, there's a little blue box there that talks about the intermediate value theorem. What it says is, if you have a coordinate or a value, say let's here, on the x-axis we're going to call that a. And then you have another value over here, and we'll call that one b. Because a is here, then this coordinate up here on this graph would be a comma f of a. And this coordinate down here would be b comma f of b. Now, what the intermediate value theorem says is if you have an interval from a to b, and in that interval, if f of a and f of b are not the same number, so that would have to be like 6, and maybe that's a -2 for the answer. If those are not the same values, this one and this one, then the function has to take on every value between this and that. So if this is 6, and this is a -2, at some point in time here, if you're following this path, you have to go to every value between 6 and a -2. Now, why is that all useful? Well, it's useful in the fact that you can use this little intermediate value theorem to determine where some roots are located. Because if you can find one that's a positive number for f of a and a negative number for f of b, then one of them has to be above the line, one has to be below, and then there has to be an intersection point with the x-axis. And that intersection point is the root. And that is everything from the second section of this chapter. You may now proceed to work on the assignment.